Welcome to Cosmos, in a pod space and astronomy series. Have you ever imagined that the universe has like built-in magnifying glasses, like things that reveal hidden galaxies, distant
They
wonders?
do, they do, they really do.
What?
It's called gravitational lensing, and it really is as mind-bending as it
That
sounds.
sounds pretty wild. So
Mhm.
what is gravitational lensing?
It's kind of like the universe is playing a cosmic game of tricks with light. Just imagine a massive object, something like a galaxy cluster, and it's warping the fabric of space-time around it. Now picture the light from a really distant galaxy trying to reach us.
Okay.
That light doesn't just travel in a straight line, it follows the curves of space-time that are created by that massive object.
So you're saying that massive objects can actually bend light?
Yeah,
I always thought light traveled in straight lines.
it does, but remember, space itself is being warped, so the light is still traveling in a straight line. It's just going through a curved space.
Ah.
It's like if you were to draw a straight line on a piece of paper, and then you bend the paper. The line is still straight, but its path has changed, right?
Right. That makes sense. Okay, so how does this bending of light create these magnifying glasses you were talking about?
So when the light from that distant object passes by a massive object, it gets bent and then it's focused, kind of like how a lens would focus light.
Mm-hmm.
And this can create a lot of different effects depending on the alignment of the distant object, the massive object, and us, the observers.
Okay.
Sometimes it creates multiple images of that distant object as if the universe is showing us the same thing from different angles.
Hold on. You're telling me we can see multiple versions of the same galaxy?
Yeah, it's really wild.
That's wild. Are there any like famous examples of this happening?
Absolutely. One of the most iconic examples is the Einstein cross. It's a quasar, and for those who don't know, a quasar is a super bright object. It's powered by a supermassive black hole,
Okay.
and it appears as four distinct images because its light is being lensed by a galaxy that's in front of it.
That's incredible.
Yeah.
So it's almost like a cosmic kaleidoscope,
Hmm.
showing us multiple reflections of the same object.
Exactly. It's a really good way to put it.
Wow. So are there other ways that this lensing effect can like manifest itself?
Definitely. So sometimes instead of seeing multiple images, we see these beautiful arcs of light. They're stretched and distorted, almost like taffy being pulled apart,
Okay.
as if the universe is creating its own like abstract art.
Uh-huh.
And sometimes if the alignment is just right, we can see these perfect rings of light. We call those Einstein rings.
Einstein rings, I've heard of those. Those sound pretty spectacular.
They are really spectacular. It's like the universe has put a giant cosmic halo around this distant galaxy, all thanks to the bending of light.
So we have multiple images, arcs of light, and Einstein rings. Those all sound pretty dramatic.
Yeah.
Are there any like subtler forms of lensing too?
You're right. Those are more dramatic effects. That's what we call strong lensing.
Okay.
But there's also weak lensing, which is much more subtle. It doesn't create multiple images or those dramatic arcs. It just distorts the shapes of background galaxies ever so slightly.
So instead of seeing like double galaxies, we're
Yeah.
seeing slightly stretched or squashed galaxies.
Yeah.
It doesn't sound quite as exciting.
Maybe not as visually stunning,
Yeah.
but weak lensing is incredibly valuable to astronomers. It's like having this cosmic magnifying glass that's revealing something we can't see directly, dark matter.
Dark matter. You mean that mysterious stuff that makes up like a huge chunk of the universe but doesn't emit or absorb light?
Exactly.
Okay.
We can't see dark matter directly, but we can see its gravitational effects. And that includes its ability to bend light. So by studying how the shapes of background galaxies are distorted by weak lensing, astronomers can map out where the dark matter is concentrated.
So we're using the bending of light to map something that we can't even see.
Mm-hmm.
It's like using shadows to figure out the shape of an invisible object.
That's a great analogy.
That's pretty cool.
And that's just one of the ways that gravitational lensing is helping us unlock the secrets of the universe. It's a powerful tool. It allows us to see things that would otherwise remain hidden, to probe the distant past, and to test our understanding of gravity itself.
That's incredible. So we've got strong lensing, creating these really amazing visual effects. We've got weak lensing, acting like a cosmic X-ray, revealing this invisible world of dark matter.
Yeah.
But you mentioned another type of lensing earlier, right?
Yes.
Something called microlens.
Yes, microlensing.
Ah.
Now think small scale. So instead of galaxies bending the light from other galaxies, we're talking about stars or even planets acting as lenses.
Hold on. Are you saying that a single star can bend light enough to create a noticeable effect?
Well, not quite like the dramatic effects that we see with galaxies. With microlensing, it's more about subtle changes in brightness.
Oh, okay.
So imagine a distant star's light being magnified by a star passing in front of it. We would see that distant star temporarily brighten as the closer star acts like a lens.
So we're looking for stars that suddenly get brighter.
Yeah, exactly. And here's where it gets really interesting.
Okay.
If that lensing star has a planet orbiting it, the planet's gravity can cause a little extra blip in the brightening pattern. It's like the planet is adding its own tiny magnifying effect on top of the star's lensing.
So we can actually detect planets using this microlensing technique.
It is. And microlensing has proven to be particularly good at finding planets that are farther away from their stars, planets that would be really difficult to detect using other methods. It's like having this special magnifying glass just for planets.
That is incredible.
Wow.
So we have strong lensing creating these spectacular visual displays. We have weak lensing helping us map this invisible world of dark matter. And now we have microlensing revealing hidden planets. This is mind-blowing. But I'm curious, how does this lensing process actually work step by step? Can you break it down for me?
Sure. So first, picture a distant galaxy emitting light, and it's traveling across these vast cosmic distances, trying to reach our telescopes. That's our starting point. The source is a light.
Got it. So we've got light traveling toward us from this distant galaxy. What happens next?
Okay, so as that light travels towards us, it encounters, let's say, a massive object along its path, maybe a cluster of galaxies. And that cluster is our lens.
Okay, so the light from that distant galaxy is going to run right into that massive galaxy cluster.
Not exactly run into.
Okay.
It's more like a cosmic bypass, I guess. So the galaxy cluster's gravity warps the fabric of space-time around it.
Right, like we were talking about earlier, space-time is kind of like this flexible sheet, and massive objects create dips in it. So what happens to the light?
The light, following its natural path, it bends. It travels through that warped space-time,
No.
and it curves around the galaxy cluster. This bending and this curving, that's what we call gravitational lensing.
Ah, okay. So the light doesn't smash into the galaxy cluster. It takes kind of a detour around it, like a car swerving to avoid a pothole,
Mm-hmm.
but on a cosmic scale.
Exactly. And the final step in this little cosmic play is us, the observers here on Earth. We point our telescopes toward that distant galaxy, hoping to catch a glimpse of its light.
And because of gravitational lensing, that light takes this curved path, and that can sometimes make the distant galaxy appear brighter or in a different position,
Right.
or even multiply it into several images.
Exactly. It depends on how the light is bent and focused by the lensing object.
That's incredible. It's like the universe has its own built-in optical illusions. It's playing tricks with light
Yeah.
and revealing things that we wouldn't otherwise see.
Yeah, it's true. And the beauty of gravitational lensing is that it's not just about, pretty pictures. It's this powerful tool that allows us to delve into, like, the deepest mysteries of the universe.
Okay, like what kind of mysteries are we talking about?
Well, for one, it's helping us understand the elusive nature of dark matter. Remember how we talked about weak lensing distorting the shapes of background galaxies?
Yeah, it was like using the lensing effect to see the invisible.
Precisely. So by studying these subtle distortions, astronomers can create these detailed maps of dark matter, showing how it's distributed throughout the universe. These maps are giving us crucial insights into how galaxies form and evolve, and how the universe's large-scale structure came to be.
So it's not just confirming that dark matter exists, it's actually showing us where it is and how it shapes the universe. That's incredible. But aside from dark matter, what other mysteries is lensing helping us to solve?
Well, it's allowing us to peer back in time, to witness the universe in its infancy.
Okay.
Remember, the farther away an object is, the longer it takes for its light to reach us, right? So when we look at these distant galaxies, we're seeing them as they were billions of years ago.
Right. It's like looking at a cosmic photo album, with each galaxy representing a snapshot from a different era in the universe's history.
Exactly. And the remarkable thing is that gravitational lensing can magnify the light from these incredibly faint, distant galaxies, making them visible to our telescopes. So it's like having a time machine that allows us to witness the universe's earliest chapters, to see the first stars and galaxies bursting into existence.
Wow. So we're not just studying what the universe is made of, we're actually seeing how it evolved, how it transformed from this hot, dense soup of particles into the magnificent tapestry of galaxies that we see today.
Absolutely. Gravitational lensing is like a key. It's unlocking the universe's hidden archives, giving us this access to information that would otherwise be lost to, the vastness of space and time.
It's remarkable. But with all this talk about dark matter and these distant galaxies,
Hmm.
is there any chance that lensing could reveal something completely unexpected, something that, challenges our current understanding of the universe?
That's a great question, and the answer is absolutely.
Okay.
While lensing has consistently validated Einstein's theory of relativity, there's always the possibility of finding these subtle deviations from predicted patterns.
Deviations. What kind of deviation?
Imagine observing a lensing effect that's stronger or weaker than what our current understanding of gravity would predict. Or, let's say we find these anomalies in the shapes and positions of lensed images, things that just don't quite add up based on our current models.
So like little glitches in the cosmic matrix?
You could say that,
Yeah.
and these glitches could be hints of, new physics, pointing towards the existence of unknown forces or exotic particles, maybe even extra dimensions beyond our current perception of reality.
So not only does lensing confirm what we know, but it also has the potential to reveal what we don't know, to push the boundaries of our understanding of the cosmos.
Exactly. And that's what makes this field so exciting. We're not just confirming existing theories, we're constantly exploring the unknown, searching for those subtle anomalies that could revolutionize our view of the universe.
I can't wait to see what new discoveries lensing will bring in the years to come.
Me too.
It's like a cosmic treasure hunt. Each new observation potentially revealing a hidden gem of knowledge.
It really is. And the best part is we're only just beginning to tap into the potential of gravitational lensing. With these new telescopes coming online and more sophisticated analysis techniques being developed, the future of this field is incredibly bright.
Well, on that note, we'll have to take a short break, but don't worry, dear listeners. We'll be back soon for the final part of our deep dive into gravitational lensing. We're going to explore some of the most groundbreaking discoveries and look ahead at the future of this fascinating field. Welcome back to Cosmos in a Pod. We've been exploring the crazy world of gravitational lensing, and it's amazing to think that something like gravity can create these magnifying glasses that reveal hidden galaxies and map out dark matter. And we even found out that it helps us discover distant planets.
It really shows how everything's connected in the universe. Something as huge as a galaxy cluster can change the path of light from a distant galaxy, light that's been traveling for billions of years, and then we get to see it here on Earth.
It's like some kind of cosmic game of billiards.
Yeah.
Where gravity is setting the balls in motion and light's showing us the paths they're taking, except the table's all warped and the balls can curve and bend in ways we wouldn't expect.
And it's not just a game. It's a tool that's changed how we understand the universe. In this last part of our deep dive, I think we should talk about some of the most amazing discoveries that have been made because of gravitational lensing.
Okay, I'm ready. What are some of the big ones?
Well, one of the biggest has been confirming that dark matter actually exists. Like we've been talking about, dark matter doesn't interact with light, so our telescopes can't see it.
Right, it's like trying to see a ghost. You might know it's there, but you can't really see it.
Yeah, exactly. But with gravitational lensing, we can see how it affects things, like how it warps the light coming from those distant galaxies. These distortions, that's the proof that dark matter is real, and it makes up a big part of the universe's mass.
So lensing gives us the evidence for this mysterious stuff. But does it tell us what dark matter is made of?
Now that's the big question. Lensing shows us where dark matter is and how it's spread out, but it doesn't tell us what it's made of. There are a lot of theories about that, from exotic particles to forces we don't know about yet.
So the mystery continues. But at least we know for sure that it's out there. And that's because of lensing. What other big discoveries have we made using this technique?
Well, lensing's also been super important in finding some of the most distant galaxies we've ever seen. These galaxies are so far away that their light has been traveling for billions of years to reach us. So we're seeing a glimpse of the very early universe.
So it's like using lensing as a time machine to see the universe when it was just a baby. What kind of galaxies are we talking about here?
But we're talking about galaxies that formed just a few 100 million years after the Big Bang. Back then, the universe was still forming. It was like the first stars and galaxies were just starting to light up.
That's amazing. It's like we're looking at a baby picture of the universe, right, when galaxies were first forming. But how does lensing help us actually see these super faint and distant objects?
Remember how we said lensing acts like a magnifying glass? Well, for these really distant galaxies, lensing can make their light stronger, so they look brighter and bigger to us than they would otherwise. And that means we can see galaxies that would be way too faint to see without lensing giving them a boost.
So it's like lensing is giving our telescopes superpowers. letting them see further back in time. What do we learn from studying these early galaxies?
By looking at the light from these lensed galaxies, we're learning a ton about the early universe. We're figuring out what it was like when the first stars and galaxies were born. We can look at their light and tell what they're made of, how fast they're making stars, and how they've changed over billions of years.
It's like putting together a giant family album for the universe, tracing galaxies all the way back to the beginning. But besides those distant galaxies, has lensing led to any other surprising discoveries?
Oh yeah, for sure. One of the most unexpected ways we're using lensing is to find exoplanets. That's planets orbiting other stars. It's called microlensing.
Wait, we can find planets with lensing. I thought it was all about galaxies and dark matter.
That's true. Those are the most common ways we use it. But remember how we talked about microlensing, where a star or even a planet can act as a lens, and that makes the light from a farther star get brighter for a little bit?
Yes, I remember. It was like a mini lensing event happening inside a bigger one.
Right. And if that star that's doing the lensing has a planet going around it, well, that planet's gravity can make a small change in the brightening pattern. It's almost like the planet's adding its own little effect to the lensing.
So it's like the planet is jumping into the picture while the star is doing its lensing thing. And we can actually see these tiny planet photobombs.
We can. And by looking at those changes in how bright the star gets, astronomers can figure out if there's a planet there, how big it is, and even how far away it is from its star.
That's incredible. So we're using the gravity of a planet to find it, even though we can't see the planet itself. It's like a cosmic mystery, and gravity is giving us the clues.
Exactly. Microlensing is really good at finding planets, especially small ones or ones that are far from their stars. It's like a special lens just for finding planets.
This is amazing. We've seen how lensing helps us learn about dark matter, see distant galaxies, and even find hidden planets. What an amazing tool.
Huh?
What's next? What's the future of lensing research?
The future of lensing is super exciting. We've got new, powerful telescopes being built both in space and on the ground. And that means even more incredible discoveries. Like the James Webb Space Telescope, it's already changing how we see lensed objects because it can see infrared light, which lets it see through dust clouds that block our view with normal light.
So Webb's like an X-ray machine for the universe.
That's a great way to put it. And here on Earth, they're building huge telescopes, like the extremely large telescope, which will have a mirror that's over 39 meters across. These next-generation telescopes will be able to see individual stars in those distant galaxies, map dark matter even better, and maybe even find tiny differences from what Einstein's theory of gravity predicts.
It sounds like we're about to enter a whole new era of lensing research. We've got better tools and ways to analyze things than ever before.
Yeah, we are. And as we keep pushing the limits of what we can do with lensing, we're going to find even more amazing things. We'll learn more about how the universe evolved, what dark matter and dark energy are really like, and maybe even discover new laws of physics that control the whole cosmos.
It's a fantastic time to be studying the universe using gravity as our guide. And that wraps up our deep dive into gravitational lensing. We started with the basics of this mind-blowing phenomena and explored how it affects what we know about the universe. We saw how it helps us uncover the secrets of dark matter, discover faraway galaxies, and even find hidden planets. We even peeked into the future where new telescopes and techniques are going to unlock even more secrets.
The universe is full of amazing things waiting to be discovered, and gravitational lensing gives us a unique and powerful way to see them. It helps us understand the mysteries of space and time and figure out where we fit in this vast cosmos.
This has been an amazing journey. I hope you've all enjoyed it as much as we have. If you want to keep exploring the universe with us, be sure to subscribe to Cosmos in a Pod and check out our YouTube channel for more cosmic adventures.
Until next time, keep looking up, keep asking questions, and never stop being amazed by the beauty and mystery of the universe.